This man is Le Châtelier, and he came up with a concept that we call Le Châtelier's principle, or the equilibrium law. This principle is amazing. It will guide you through the entire rest of chemistry and is applicable to many other subjects and your life. We'll talk about your life later. What is this principle? The fundamental idea is that if you induce a stress on a system at equilibrium, the system responds to offset that change. Recall that equilibrium is the concept that the rates of the forward and reverse reactions are equal. Reactants are becoming products, and products are becoming reactants. The amount of products and reactants don't have to be the same. Think of it like a border crossing. Let's say there was a law that the number of people who go from Canada to the US each day has to equal the number of people who travel the other way, from the US to Canada. If 1,000 people travel from the US to Canada and 1,000 people travel from Canada to the US, then the net number of people lost or gained is 0. The rate of people crossing the border is the same. However, we all know that the US has many millions more people than Canada. The US has around 319 million people, whereas Canada has around 35 million people. While the rate of border crossings may be the same in this example, clearly the number of people in each country is not. This is the idea of a dynamic equilibrium. People are constantly moving across the border in both directions at the same rate, but the relative populations aren't necessarily the same. If every person were a molecule, it'd work in a similar way. Now here's the same analogy applied to Le Châtelier's principle. For the sake of simplicity, let's say there's one border crossing. When the system is in equilibrium, this method works. It's peaceful. There are 3 main ways to disturb the equilibrium: change the temperature, the concentration, or the pressure. I'll apply the analogy to the concept of changing the temperature. A stress is induced on the system, and we have to figure out which way the position of equilibrium shifts. This means, how does the system change when you induce a stress? Say we have an exothermic reaction. This means that heat is produced. Think of exo like exit, and therm is heat, so heat is leaving exothermic. A convenient way to think of this in terms of equilibrium is to treat heat as a product. Heat is produced, just like products are produced. If you have an endothermic reaction, heat is required to make the reaction run, so you can treat heat like a reactant. Now back to our analogy. Let's say that the reaction of people going from the US to Canada is endothermic. They have to drive so far that they create a lot of heat with all the transportation and greenhouse gases. Heat is required for people to get from the US to Canada, so let's treat it like a reactant. We're at equilibrium when all of a sudden the weatherman announces that a huge snowstorm is coming to Canada. The temperature plummets and the people are freezing. Many of them want to flee south. The border guards are overwhelmed, and more people leave Canada than enter it. The system is no longer at equilibrium, as the rate of people going over the border in each direction is not the same. It has shifted toward the reactants. Why is this? If we look at the chemical equation, heat is on the reactant side. If we decrease the temperature, we lose heat. If we lose some reactant, the equilibrium will shift to try and make more of it, to recreate balance. Eventually, after the storm passes and equilibrium is reestablished, the rates of reaction will be equal. But now, there are a few thousand more people in the US than there were before the storm. Let's try shifting the other way. A heat wave hits the US and people want to travel north. More people go to Canada than leave it, and the position of equilibrium shifts toward Canada, towards the products. This is because when the temperature goes up, since heat is treated as a reactant, the position of equilibrium shifts to the right, toward the products. Let's look at this with our molecular example. This reaction, combining nitrogen and hydrogen gas to create ammonia, is called the Haber process. This process is exothermic, as delta H is negative. Therefore, heat can be treated like a product. If you increase the temperature, the reaction will shift to the left, away from the products. If the temperature is decreased, it's as though products are lost, and the position of equilibrium will shift toward the products to create balance. Another way to induce stress on a system is to change the concentration of the products or reactants. Let's use a generic example. If we add a bunch more of compound A, our concentration of A, one of the reactants, increases, and the position of equilibrium shifts right toward the products. An expression can be written for the equilibrium that looks like this. K is the equilibrium constant. Sometimes you'll see K with a subscript, but for now we'll just keep it simple with K. This expression has K equal to the concentration of the products divided by the concentration of the reactants. K has a value specific for that reaction at a certain temperature. Another similar expression is this one. The only difference is that the K is replaced with a Q, which is called the reaction quotient, Q for quotient. This describes a reaction that is not at equilibrium. If some of reactant A is added to the system, notice what happens to the equation. A is in the denominator. Increasing the denominator decreases the value of Q. Now Q is less than K. The system wants to shift to reestablish equilibrium. Since Q is less than K, the system will shift right to produce more products and consume more reactants. This will cause Q to increase until Q equals K, and the system is at equilibrium once again. This equation will help you understand what's happening when the concentrations of reactants and products change. Imagine you have 30 rowdy kids in a small classroom with only one small door to leave. It's a little crazy, but the teacher can manage it. Now add 30 more kids to the same classroom. It's insane! The concentration of kids doubled. The system is stressed, not to mention the teacher. Papers and books are flying everywhere until the teacher opens a door to recess and many of the kids leave. Eventually, the number of kids outside and inside is such that the place is less crazy and the number of kids coming inside is the same as those leaving. Equilibrium is reestablished. The third main way to induce stress on a system is to change the pressure. This is important in a gaseous system where pressure plays a significant role. Solids and liquids are not very affected by pressure, but gases are. Let's use this example from earlier of the Haber process. How does pressure affect equilibrium? First, identify which compounds on each side of the reaction are gases. In this case, all three compounds are in the gas phase. Then add up the coefficients of the reactants. Then add up the coefficients of the products. There are 4 moles of gas on the reactant side and 2 moles of gas on the product side. The rule for pressure is that increasing the pressure pushes the position of equilibrium toward the side with fewer moles of gas. Decreasing the pressure has the opposite effect. In this example, increasing the pressure pushes the reaction to the right, toward the products. You can use an equilibrium equation to visualize this mathematically. Imagine the classroom analogy. If suddenly the room full of 30 kids decreased to half the size, the system will become much more stressful, and the teacher would want to shepherd those kids out to recess as quickly as possible in order to reestablish equilibrium. This is the idea of how Le Chatelier's principle applies to equilibrium. The Haber process provides a good look at all 3 ways to shift the equilibrium. Recall that this reaction is exothermic, so heat can be treated as a product. If the temperature is decreased, the reaction will shift right. If the pressure is increased, the reaction shifts toward the products. Therefore, higher pressure will have a higher yield for this reaction. Of course, increasing the concentration of the reactants will shift the position of equilibrium toward the products. It seems that, to obtain the greatest yield, you should put a lot of nitrogen and hydrogen together at a very high pressure and a low temperature. All 3 of these conditions would push the position of equilibrium toward the products. However, high pressures cost more money, and lower temperatures slow the rate of reaction, as you'll learn in kinetics. So there's a balance of high yet economical pressures and low temperatures for equilibrium, but high enough for the rate of reaction. This is a careful balance that has been solved by chemists and chemical engineers in order to provide the best yield for ammonia. And we're lucky too, because this is a great way to fix nitrogen and provide fertilizer. In fact, the Haber process is said to provide fertilizer to feed half the world, which means that 50% of the nitrogen in your body comes from this process. Now that's chemistry in your life at the deepest level, and it's all possible thanks to a healthy understanding of equilibrium and Le Chatelier's principle.